Welcome to the next lecture in the Software Design and Modelling course. And today we're going to start talking about modelling and how it fits into design a bit. So here is the rough plan. I'm going to start off by saying something about what we even mean by modelling in software design and in software engineering more generally. And I will say a few words about why it's important, and in order to set the scene for what we're going to go on and talk about, I will say something about the history of modelling in software engineering and how things have changed, and at the end lead into some of the required reading by mentioning some of the diverse uses of modelling in current software engineering practice. Let's get one triviality out of the way before we get started properly, because it often confuses people. You'll see these two spellings. You'll see modelling written with two L's and with one L, and this is an instance of a general pattern which is a difference between British English and American English. Generally speaking, because I'm British and I'm a pedant, I use British English spelling, but the one exception is that when we spell out UML, the Unified Modelling Language, in full, it always has one L. Why is that? Because Unified Modelling Language is a trademark, and so we spell it in the American way, even in the UK, because it's a trademark and it comes from America. So that's why you'll see me being slightly inconsistent. I apologise if I'm inconsistent in any other way. No, you will not lose marks for spelling modelling wrong, at least not if you use one of those two spellings. While we're at it, a lovely shibboleth that people often don't know about, look up shibboleth, by the way, if you don't know the word. It's not object-orientated, even if you're British. It's object-oriented, okay? This is one of those things, it doesn't matter at all, except that if you say object-orientated, people will assume that you don't know anything about object orientation, because everybody who does says object-oriented, so just get that right. From time to time I spot places in the university's course descriptions and web pages and so on where they accidentally say object-orientated, thinking that that's the correct British way to do it, and sometimes I point things out and even more rarely they actually get changed. You could do that too if you noticed any cases. Anyway, on to the more interesting stuff. What is a model? So here is my favourite one-sentence definition. A model is an abstract, usually graphical, representation of some aspect of a system. You'll come across in other places the idea of descriptive models, where you start off with some very complicated system, whether it's a piece of biology or what have you, and you describe how it works. The models that we're talking about in this course are prescriptive rather than descriptive, which is to say they say something about how a system should be. They're usually models which are built during the course of development, before the system itself really exists, and one could get into some interesting philosophical issues about the implications of that description, but at least just for now be aware of it. Models are an important current topic of research. There's a large amount of literature about it, and of course fashions change and people focus on different aspects of models at different times. I'm going to give you the abstract of a paper on the next slide. Don't read ahead. Ask yourself when the paper dates from. Okay, I shall read it out. Iterative multi-level modelling, a methodology for computer system design. The paper presents a method of modelling a computer system design as it evolves, so that evaluation can be made an integral part of the design process. The paper introduces the concept of concurrent existence within a single model of several representations of the system being modelled at differing levels of abstraction. Thus, important design decisions are expressed directly in terms of appropriately abstract quantities, facilitating understanding, validation and modification of the system design. The paper includes brief details of an experimental implementation of the modelling technique and of the use of the technique to model both hardware and software components of a multiprocessing system. Okay, pause the video if necessary. Write down a date. When do you think that this dates from? Usually I ask people to show their hands, but you can't do that this time. Okay, this is from 1968. It's from 1968, a conference that was held in Edinburgh, the IFIP conference. And in a sense, This is just saying there's nothing new under the sun, because most of these concerns could equally well occur in an abstract of a paper about modelling today. We're still very much concerned about having different representations of a system at different levels of abstraction. This is a standard way of using modelling. And we're interested in doing it in order to be able to express important design decisions in the models in an appropriately abstract way, in order to be able to understand the system, to check it, that is to validate it, and to make it easier to modify the system design as we go on. This is what modelling is about to this day. Okay. In fact, the biggest tell, I think, in this abstract is probably the use of the outdated term multiprocessing system. But there you go. So let me go back again for a moment and revisit our one-sentence model now that we've seen that this kind of idea has been around for quite a few decades now. So a model is an abstract representation of not of the whole of a system, but of some aspect of a system, which is to say that what we're doing is we are abstracting out some information that is not relevant for the purpose for which the model was developed. So the idea is that the model will support the work of some person or some group of people by allowing them to focus on the information that they need in order to understand how to make their decisions and in order to record what their decisions are. This is important because of what I said earlier about software systems involving much too much information for any individual human to hold them in their head. Okay. So that's why we need abstract models. It's in order to have something that gets rid of enough details that the remaining information, the stuff that somebody actually needs, can be held in their head for long enough and well enough for them to actually make decisions. And it turns out that graphical representations are, for some purposes, some of the time, helpful in kind of being a good match with people's cognitive abilities to help them to visualize the system and understand what's going on. We'll have quite a lot more to say later about textual models versus graphical models, and you'll see both of them. And it turns out that the distinction is not as important as we once thought, I would say. I think in the early days of object-oriented modelling, there was a feeling in the community, both the academic community and the industrial community, that the graphical nature of the models we were using was really important. These days, I think we'd be much more likely to say that you can have graphical and textual representations of the same model, of the same syntax, because we now have a better understanding of the ability to draw a distinction between the concepts that are represented in a model and the syntax in which those concepts are represented, which turns out to be a very useful distinction to have in mind. Okay, so why do software engineers model? Well, people find it psychologically natural to visualize software somehow. So what you'll find is that if you don't provide people with a modeling language, you don't teach them a modeling language, but you do put them in an environment where they have to communicate with one another and make decisions about software, people make up their own modeling languages. People start drawing pictures in an ad hoc way on the backs of napkins or whiteboards or what have you. And so what we're doing in modelling in a sort of organised, standardised way is to try to enhance the value of that activity by modelling in a way which it's easier for people to learn to understand and to understand precisely. So visualising software, or enough of the information about the software, can help the person building the software to keep it straight in their head and to therefore make decisions and check that their decisions are appropriate and record what they are in a reasonable way. And they can help, visualizing the software and using models can help communication between groups of people, whether that's developers talking among themselves about how to solve some particular design problem, or whether it's developers talking to customers about decisions that have been made about a software system so far, and whether those decisions do indeed correctly reflect the customer requirements. In deciding how to do it, we have a tension between flexibility and standardization. Okay, so if you just say, oh, we won't have any choice of modeling language, we will just let developers make up whatever notation they like on the whiteboard whenever they feel like it. You've got ultimate flexibility. Okay, somebody can use whatever notation seems to be appropriate to their needs at that moment, but you have no standardization at all. On the other hand, if you say everybody is going to use this completely formally specified modeling language in this one tool, and they'd better use it precisely correctly, then you're right over at the standardization end of the spectrum. And there really is a tension between these things. Both aspects, flexibility and standardization, have their benefits. Flexibility, obviously, in allowing you to have a notation that precisely reflects your needs at that moment, and standardization in avoiding the risks that are associated with somebody else failing to understand what you mean, or worse, thinking that they understand what you mean, but understanding something different from what you meant to express. We also have a tension between the notation having an obvious meaning, so for example having a notation which is quick and easy to learn and which people have no difficulty in understanding the precise meaning of, versus something being precisely expressive. So this is largely about, to what extent do we want to be able to say, no, that model is wrong, you are using the modelling language incorrectly. People sometimes find it a bit surprising that it's even possible to use a graphical modelling language incorrectly. There's a tendency to imagine that while we're all very familiar with the idea that you can have bugs in your program, you can write a thing which is almost a Java program but actually incorporates a syntax error so that it isn't really a Java program. People somehow don't expect the same thing to happen with diagrams, but they do. It's very easy to draw a diagram which is almost a UML diagram, but not quite, because it contains a syntax error. And the possibility of doing that is really quite parallel with the corresponding features in programming languages. It's an unwanted side effect of the existence of a precise meaning of what you write. And it's unwanted because nobody ever likes to make mistakes, and we attack it in much the same way. So just as with programming languages, you wouldn't sit down in a plain text editor, I hope you wouldn't sit down in a plain text editor that knows nothing at all about your language and expect to type your program without error. You're much more likely to use an integrated development environment, or perhaps a smart editor that has some kind of idea about how to pick up at least some of the errors that you might naturally make when you're typing a program, perhaps even to save you some typing by allowing you to use auto-completion features or what have you. And these days, not always but very often, the kinds of tools that support graphical modelling will have the same kind of features. We'll try to give you the affordances that let you build correct models more easily than incorrect models. It wasn't always thus, of course. Let's, on the next few slides now, look a bit at the history of modelling in software engineering. So, of course, graphical modelling has been around since long before software, never mind software engineering. There have been organisation charts. You're less likely to have come across PERT and CPM diagrams these days, but they used to be very popular. Program evaluation and review technique, critical path method diagrams. You've all seen Gantt charts, I'm sure, for planning projects and the dependencies between tasks that have to be done within a project. You've probably seen genealogy diagrams, where you say, here's a person and here are their parents and here are their parents and so on. And these kinds of graphical models were used as analogies in early papers, and so modelling software was seen as a natural development from modelling other things which had been done before. The earliest real software engineering diagrams tend to be data-oriented. They're about how the data is going to be organised within a system, and that's still a thing that gets done. A key thing which has varied over the decades since software engineering modelling was first invented is size. So in the early days, this counted as a very large model, and it was described as such in a paper by Bachmann in 1969. These days, this is not a very large model. These days, a very large model is probably one with tens or even hundreds of thousands of blocks, might represent classes or what have you, in them. But we have with increasing tool support and with the general increase in ambition for our software systems, become also much more ambitious in our use of models. You might reasonably say, doesn't the use of very large models negate part of the benefit that we're trying to accrue through using models in the first place, namely allowing humans to apprehend enough of the information about their software to make appropriate decisions? And the answer to that is, well, yes. Nobody, of course, is going to hold in mind the whole of, probably even not really the whole of a model that size actually on the slide, certainly not one that has tens of thousands of classes in it. But all this says is that, remember that this mention of kind of multi-level, different models of different purposes, multiple levels of abstraction of models. This also occurs in large models that we use today. So you might just zoom in and look at a small local fragment of a very large model, or you might abstract a very large model further and actually in practice work with something which is a more abstract model than the very large one. Various different things that you might do, and we'll see some more about that as we go through this course. Okay. Early on, there's kinds of models of data, the static structure models that were used. Those two are not quite the same thing, are they? But anyway, they're related, and they both were around very early on. Those models early on used to be seen as pictures rather than as formal objects, and it's quite interesting to look at the old papers from those days and see the understanding of what models really are evolving. So there's a nice paper by Chen in 1976 which really emphasises the idea, and I think it's emphasised because it was a relatively novel idea at that time, although I've not done an exhaustive investigation into the literature, that a diagrammatic representation could be isomorphic to a symbolic one, so that just because it was a diagram didn't mean that it was any less formal or any less open in principle to formal manipulation than a model that was written down using Greek letters, which these days is a completely mainstream idea, and we have appropriate techniques for supporting that kind of manipulation, which makes it even more obvious that we can do it. The other main class of models, besides the static structure models that tell you about either the data that's manipulated by a system or the way the system itself is structured, or both, the other main class of models is dynamic models, and these too predate their use in software. There have been flowcharts used. There's an example from 1921. Automata go back to the early days of computers at least. Harel state charts were invented in the 1980s and have been enormously influential, including on UML itself, and similarly message sequence charts, which began in the telecoms industry and are now in the guise of sequence charts in UML and elsewhere, much more widely used across the software engineering domain. So modelling software has always been around, as long as software has been around. However, it really took off with the rise of object orientation in the 1990s, and hence it became identified with object orientation. So probably, I mean, these days it's quite hard to find a whole lot of software development that isn't object oriented, really. But you are far more likely to come across the use of graphical models in software design in your Java course than in your Haskell course, for example. It's something that goes along with object-oriented approaches to software engineering, largely, I think, for historical reasons rather than for any kind of essential reason, though we could discuss that. So in the 1980s and the early 1990s, object orientation was the fashionable silver bullet. It was going to finally solve everybody's software problems, because objects were wonderful, and they were going to allow you to have a structure in your software system that would precisely reflect the real world. They would solve the reuse problem. They would mean that you would never have to write another customer class again, because the customer class that you wrote in one system would be the only one your company would ever need. And you can probably tell from my tone of voice, as well as perhaps from your own experience, that it didn't turn out quite like that. I think it is fair to say that object orientation has been an enormous step forward in software engineering. I think it's a very good thing, and there are very good reasons why modern programming languages these days are highly likely to incorporate at least some kind of notion of objects. It's genuinely a very useful concept. However, it did not make all the problems of software engineering go away, as we now very well know. Okay. During this explosion of object orientation, the idea was being sold that if you used object-oriented programming, design would be very much easier because of this way in which there would be a correspondence between the classes in your system and the concepts in the domain and in the real world. And this idea was driven home and supported by the use of graphical models to represent the high-level structure of your system and that correspondence between domain concepts and classes in your system. And there were a whole bunch of gurus, famous experts in object orientation, and roughly speaking, each one had their own company which sold their own tool, their own modelling tool, wrote their own book, and had their own modelling notation. So three who have had their names preserved through the time since then are Booch, Rumbaugh and Jacobson, the three amigos who were the main originators of UML, the Unified Modelling Language. But there were many others, so Code, Odell, Schleyer-Meller, Wirfs-Brock, each had their own approach with their own strengths, and some of these we'll come back to, especially as we start to talk about the design process later on. Schleyer and Meller were pioneers in the idea that you could use your model to generate your code from it, that you didn't have to develop a model and then as a completely separate process write the code. Rebecca Wirfs-Brock is particularly important for responsibility-driven design, which is something we might well come back to later. Okay, so they all had their own tool and notation, and this was kind of a problem because what it meant for you as a company that wanted to adopt object orientation and adopt graphical modelling was that you had to make this major decision about which camp you were going to get into, which tool were you going to buy, which notation were you going to train your developers in. And if you got it wrong, then switching was very hard. So not only did you have to buy a new tool and retrain your people, but also you probably now had models of your existing business critical systems, and what were you going to do with those? Were you going to translate them into your new choice of notation, or were you going to put up with the fact that you now had a mixed economy of models in different incompatible notations that you perhaps had to continue to refer to? It was difficult. So there was lock-in for companies. And that was a problem. And so there was a push for unifying these approaches. OMG, the Object Management Group, was and is an organisation with many tool developers as members, but also many companies that are using object-oriented techniques of various kinds. And they pulled the community together into standardizing the Unified Modelling Language. The first version of that came out in 1997. There's kind of an interesting story there, but I think I come back to it in a few lectures' time. For now, let me just say the original idea was to unify not just notations, but, as that quotation indicates, methods. So the idea was that Booch and Rumbaugh, later joined by Jacobson, would convince the world to develop software the way they said it should be developed. And that got a lot of pushback because people quite rightly said there's quite a lot in common between the kinds of domains that you're working in, and some of our domains are really quite different and need a different approach to software development. And it proved to be much more feasible to standardize on a single notation than to standardize on a method. But the idea of standardizing on a development method didn't completely go away. Anyway, so we had an early version of UML in 1997, and then it got gradually developed over the years. There was a major change between UML 1 and UML 2, which one could argue, and I think I might argue, was a bit of a missed opportunity. So one of the problems with UML 1, was that it had lots of inclarities and confusing bits in its definition of what the notation actually meant and what you could write. And there was quite a lot of dissatisfaction about that. And at one point it looked as though UML2 would clear all of those up and would give us a precise modelling language of comparable kind of well-definedness to programming languages that you're familiar with, so that there would be no argument about precisely what does this diagram mean and is this one correct or not, which would in turn make it much easier for people to switch between tools. They wouldn't run into problems where two different tools had a slightly different interpretation of the same diagram, for example. In fact, what happened was that UML2 wasn't really, in ways that mattered, any more precise than UML1, but it was much, much larger. And I think it's arguable that that is really why UML, although as I say on the slide it's now completely mainstream, I'll say more about what I mean by that in a moment, has not perhaps achieved the level of success that we might once have hoped for it. So you, as students who might want to do software engineering, I think you do need to know some UML, but it's not something that you will see given as an essential skill in job advertisements, and there are lots of backlash against it, with people saying nobody uses UML. This is kind of not really true. In fact, UML is now so mainstream that even people who think they're not using UML are using UML. And you can see this if you look at things even so basic as how one represents classes in an object-oriented system and the relationships between them. I'm sure you've seen this done. In fact, you've probably seen it done in your object orientation course. But these days, if you're going to draw a picture of a class, you're going to draw a rectangle, right? You've seen that. Okay. It wasn't always thus. The early notations didn't, by no means did all of them use rectangles to represent classes. There were clouds, that was in the boot notation, and ellipses and all kinds of other things. So just a bunch of kind of small things that you just assume, you sort of think about this as being a natural way to represent software. It's gone into the standard vocabulary that you grow up with if you learn to develop software and you read books about developing software and so on. But actually quite a lot of this stuff that now seems to be part of the air we breathe and the water we drink actually came out of UML. And we'll do some more criticism of UML later, but let's not do it right now. So, in as far as we got a unified modelling language, the flexibility standardization tension that I mentioned before has, for now in the mainstream at least, been resolved in the standardization direction. Okay, a language was standardized, even if perhaps not as precisely as we might have liked. There are mechanisms for customizing UML if you want to get some of that flexibility back, and if you want to get a lot more flexibility back, then you might turn, instead of to a general purpose modeling language like UML, you might turn to a domain-specific modeling language, and we'll have a lot more to say about those later on. So good things about resolving this tension in the direction of standardization are that we now have a thriving tools market, so there are thousands of different tools supporting UML at all different price points, and some of them are online and some of them are integrated with integrated development environments, and others are freestanding, and so on and so forth. We get a certain amount of mobility, both of people and of projects, although because the language is not perfect for all purposes, and because it's not perfectly precise, we don't get quite as much mobility as we might have expected. UML is used differently in different projects, and moving your project from one UML tool to another is, despite attempts at standardization of formats and so on, is not nearly as easy as we might once have hoped it would be. And this kind of critical mass has enabled the development of a whole lot of techniques and new kinds of tools to work on UML. In the early days, this was largely about stuff like verification. If you're going to do some kind of model checking or performance analysis on your system at the design stage before you've actually got implemented code, you can have some hope of being able to do those kinds of things using a UML model as input, and that's a really exciting thing to be able to do. And by the way, of course, it requires a UML model to be a formal artifact, the kind of thing that you can actually feed into a verification tool. It won't do for it just to be a picture. And later on we'll see that UML and also the dissatisfactions with UML have led us on to the field of model-driven development, which is, I think, something with some very exciting prospects for the future. The bad things about standardization on UML are, well, you all have to learn UML, and that's not as easy as it might be. The need to establish a consensus, because so many people had to buy in to UML, this has led, I think it's fair to say, to bloat in the language. This is why it's so big. It's because in order to get the major players to buy into using UML and not persisting with their own pre-existing modelling language, everybody's favourite features had to get added to the language, and this is why UML is the opposite of concise. There are many different features that aren't really completely orthogonal. If an individual designer had designed UML, it wouldn't have looked like what we've got at all. This is absolutely designed by committee. And the other aspect of that is it's very hard to change. So I think I mentioned UML 2.5 in 2015 a little while ago. I forget which minor version we're at this point, but it hasn't changed very much since then. And that's a good place to stop for a moment, so I will.